Welcome back to Integral Calculus. This video is a competitor for the longest title in the course, although there's another one coming up soon that gives it a run for its money. Anyway, we're going to be talking about the derivatives of inverse trigonometric functions. At its heart, today's lesson is just a couple of simple differentiation rules to learn and apply. The interesting thing here is thinking about where they come from and the link to working with inverse functions in general that we've established previously. Let me get my head out of the way and let's talk about sine. A couple of things we know about sine. We know that the derivative of sine of x is equal to the cosine of x. And we know that sine squared of x plus cosine squared of x is equal to 1. And then in general, we know that the derivative of f inverse of x is equal to 1 over f prime evaluated at f inverse of x. And one of the things we saw when we've worked with inverse functions before is that dealing with the variables tends to be the messiest part. So let's come back over here to my discussion of sine and replace all of my x's with thetas to stress that this is where we put the angle in the trigonometric function. With that change in notation, I can now take my arcsine of x is equal to theta as the notation that sine of theta is equal to x. Now here's where I'm going to start having fun, and it's not going to be immediate apparent why I want to have this fun, but I'm going to have a little bit of fun here with the Pythagorean identity. If sine of theta is x, then sine squared of theta is x squared. And we can rearrange and solve for theta and say that cosine of theta is plus or minus the square root of 1 minus x squared. Now, from here, things can get a little bit messy with the plus or minus, and I don't want to deal with it. So I'm just going to assume that we're going to deal with an angle in quadrant 1. And the reason I'm going to assume that is that it makes sine and cosine always positive. And that's just going to make the derivation a little bit easier. And then once we get through the rest of it, we'll generalize and figure out what could have happened in other cases. Okay, that's everything we need, because now we can establish that the derivative of arcsine of x is 1 over the derivative of sine evaluated at arcsine of x. I just established arcsine of x is theta. And I also established that cosine of theta is the square root of 1 minus x squared. Let's copy the thing we've been differentiating here. Which is just going to make things a little bit easier when I scroll the rest of it off the screen. Right. I hope that when you're looking at that, you're thinking that seems a little bit weird. I started with inverse trigonometry. And if I want to take the derivative of an inverse trigonometric function, I get a radical. In terms of complexity, inverse trigonometric functions I generally think of as some of the most complicated functions that we've dealt with up to this point in mathematics. And I mean, sure, radicals are not particularly straightforward, but they are several orders of magnitude more straightforward than trig, let alone inverse trig. And yet, when we take the derivative of inverse trig, we get a radical. It gets even better. I'm not going to go through the process again, but you can do the same thing with any of the other trigonometric functions. And I specifically want to point out that when you do this with the inverse tangent, you don't even get a radical. You just get a rational, 1 over 1 plus x squared. As they go, that's one of the more straightforward expressions that we might want to deal with. All right. But I guess we should generalize those a little bit, because usually when we're dealing with differentiation, we are not so lucky to just have a function evaluated at x. Usually we're going to be dealing with some sort of a composition where there is something interesting in the argument. But just applying the chain rule, and then let's fill in some more functions. Finally, when we get down here to arcsecant, we start to see something approaching the level of complexity we probably were expecting. The derivative of arcsecant of u is u prime over the absolute value of u times the square root of u squared minus 1. And as messy as that is still not that bad. For the sake of brevity, I'm not listing out arc cotangent or arc cosecant. 9 times out of 10, sine and cosine are going to take care of everything that you could possibly need in trigonometry. Almost all of the rest of the time, tangent is going to take care of what's left over. And then because tangent and secant are related to each other in the Pythagorean identity, right, what is it? Tangent squared theta plus 1 is equal to secant squared theta. Whenever tangent shows up, it's always possible that secant won't be too far behind. Right. In theory, you could work with cotangent and cosecant. There are reasons that you might want to look those formulas up, but I think I've talked about them more in this video than you're going to talk about them in the rest of the course. All right, 4 new rules, that's not too bad. Then it's just a matter of applying them. All right, let's quickly look at a derivative here. And why not jump right off the deep end and go into something fun, like the derivative of arcsine x plus x times the square root of 1 minus x squared. Nice, simple, straightforward expression to lead us off. All right. Yeah, I have no idea where something like this would come up. This is about as ugly as I could come up with, just to play around with and see that, as always, calculus is really all about the algebra. But our differentiation rule says that the derivative of arcsine is 1 over the square root of 1 minus x squared. Then I have this square root here. It's a product of two functions, so I'll use the product rule. Derivative of x is 1, so we'll have the square root of 1 minus x squared. And then we will have x times the derivative. The derivative. My accents are all on the wrong syllables. The derivative of the square root of 1 minus x squared is going to be 1 over 2 times the square root of 1 minus x squared times the derivative of the stuff inside, which is minus 2x. And at this point, you start to notice that, well, this square root is showing up all over the place. So we can find a common denominator. We can simplify across the numerators. So we'll have 2 plus 2, which is 4. We'll have a minus 2x squared and another minus 2x squared, which is minus 4x squared. Drag out that common factor of 4 in the numerator. Four over 2 is, of course, 2. And then 1 minus x squared over the square root of 1 minus x squared. We just did the opposite of that up here in finding the common denominator in the first place. That is, in fact, the square root of 1 minus x squared. All right, something a little more peaceful for you to try. Why don't you take a couple of minutes and differentiate the arctangent of 2x. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.